ethanol. So the first question, we got to figure out what kind of reaction is this going to be. So what kind of alkyl halide do we have? What kind of alkyl halide do we have to start with here? Secondary, and just secondary. So does that eliminate anything? Nope. Thanks for nothing. Then we want to look at the nucleophile, or base. What kind of nucleophile or base do we have here? It's unreactive and small. So unreactive for sure makes us think what? We know it's going to be either SN1 or E1. When we see it's small, that maybe makes us think SN1, right? Now, could E1 happen? Absolutely. SN1 and E1 are going to be like, there's always going to be like a mixture of products. So usually what I would do in a question, I would say, now read directions very, this is part of reading directions very carefully, right? For the substitution reaction below, for the elimination reaction below, if I say that, I'm telling you what kind of reaction it is. I'm not taking the guesswork out of it at some level, right? So be very careful to read the instructions. Don't get in such a rush, right? Read those instructions. Okay, so SN1 or E1, we're not going to worry about it right now because we're going to get to that same kind of intermediate carbocation, and we're going to do some rearrangements today for these carbocations. Then we'll worry about what the products would be if it was SN1 or E1, right? So let's just do the first step in the mechanism. So what's the first step going to be here? Whether it's E1 or SN1, same first step. What's it going to be? The bromine leaves, right? The rate determining step, the formation of the carbocation. Why is that the rate determining step? So why does it take the most energy and why is it the slowest? Right, carbocations are high in energy, they're very reactive. Why are they very reactive and high in energy? Why are they unstable? The octet rule. So the octet rule is a thing. Carbocations don't have a full octet, right? So saying the octet rule is not the answer. Saying that carbocations do not have a full octet, which makes it less stable and more reactive, and that's why it takes more energy to form it. That's why is the rate determining step. Awesome. Balance my charge. Br minus. If I make a carbocation, what do I need to immediately think about? I need to think about those beta things, sigma bonds 2 bonds away, and I need to think about rearrangements. I'm only going to do a rearrangement if I form a more stable carbocation. So this is where numbering is important. 1, 2, 3, 4, 5, 6. Is there anything 2 bonds away, 2 sigma bonds away from the carbocation that I could move to make a more stable carbocation? Because I'm only going to make a more stable one. I'm never going to go uphill. I'm only going to make a more stable one. So this is a secondary carbocation. So how many hyperconjugation buddies does a secondary carbocation have, this one? How many hyperconjugation buddies? I see 1, 2, 3, and then the unwritten hydrogens are still there. 4, 5, and 6. Right? Sigma bonds 2 bonds away. There's hydrogens here, right? They're just not drawn in. They're there. So I have 6 hyperconjugation buddies. Which one of those buddies can I move to make this more stable, to make a more stable carbocation? Should I move a hydrogen on carbon 1? Or what can I move on carbon 3? The methyl. Does it matter 4 or 5? They're the same. Doesn't matter. So I'm going to do a methyl shift. Right, the 2 electrons in that carbon-carbon bond and carbon 4 are going to go to carbon 2. So that rearrangement. So now, what new bond did I form? What new bond did I form and what bond did I break? I broke a sigma bond. I didn't form a pi bond. Carbon 2 is bonded now to what? Which carbon? Carbon 4. 1, 2, 3, 6. There's 4. There's 5. Where's the plus charge? Where's the carbocation at now? It's on 3. Awesome. Now what kind of carbocation do we have? pretty good. Could I make a more? So now, but I still need to look, right? I need to make sure. Let's look for those sigma bonds 2 bonds away. So I could go back to carbon 2. I could move a methyl back, but that'd be making a secondary. I guess I could move an H, and that would make a tertiary, but that's a sideways move, right? What about these 2 hydrogens bonded to carbon 6? Should I have those rearrange? Now be careful. Look at carbon 6. What's carbon 6 next to? Carbon 6 is next to the benzene ring. We'd call this the benzylic carbon. If we could have a carbocation in the benzylic position, is that good or bad? That's good. Why? Because then it could do resonance with the ring. So yes, this is a tertiary carbocation, but if I move this hydrogen over, I'd make a benzylic carbocation, which is better than a tertiary carbocation because this can do resonance, right? This is good. This is stable. But right, we talked about ways to stabilize carbocations. What are the 3 ways to stabilize carbocations? Hyperconjugation, pi bond resonance, and lone pair resonance. Hyperconjugation, while okay, it's not as good as pi bond resonance, right? How many hyperconjugation buddies does this tertiary carbocation have? How many hyperconjugation buddies does it have? Sigma bonds 2 bonds away. How many does it have? 1. Mystery CH is not there. 3, 4, 5, 6, 7, 8, 9. A tertiary carbocation has 9 hyperconjugation buddies. That's why it becomes more stable than a secondary. There's more hyperconjugation, makes you more stable. But pi bond resonance is better than hyperconjugation. So what's going to happen? This H is going to shift and rearrange. You're going to break that carbon-hydrogen bond and make a new carbon-hydrogen bond and make a new carbocation. So now where's the plus charge? Oops, 4, 5, 6. Where's the plus charge? Carbon 6. Now, that's a really stable carbocation. It's hard to get much better than that. Benzylic, right? At the bottom, it's the most stable. It's secondary in benzylic, right? Still pretty good. Only thing that could be better would be tertiary in benzylic, and I can't make that happen, I don't think. So you have 2 rearrangements there. Now we can start thinking about E1 and SN1, right? So now we bring back in, Br minus has been along for the ride, right, the whole way. And then the solvent is also around. So what do you guys want to do? You want to do E1 or SN1? Let's do E1. So we have a carbocation. We're gonna make this an E1 reaction. We need to look for what? Beta hydrogens. What kind of beta hydrogens? sp3 beta hydrogens. How many so if this carbon's the alpha carbon, the one with the carbocation is the alpha carbon. Beta is 1 bond over. How many options do we have? How many? Just the 1, right? There's no hydrogens on this, and if there were, it wouldn't work because what's the hybridization say of this carbon? It's sp2. So it's just gonna be carbon 3. So there's an H on carbon 3. Heck, it's the H we just moved, right? All right, it's the H we just moved. So we're gonna take that beta hydrogen, and we could either use the bromine or the solvent. It's up to you. Which one do you want me to use, bromine or the solvent? Let's use the solvent. There's a lot of solvent around. Let's use the solvent. Solvent's going to take that H, make an alkene. Do I need to worry about being anti-periplanar for an E1 reaction? Nope. Don't worry about anti-periplanar. Don't worry about that. What about, there's only one type of beta hydrogen, so can I choose I can't worry about the more substitute, right? There's only one type, so there's no choice there. What's the other thing I can choose, though? about an alkene. So I can't choose if it's more substituted or not. What's the other part that I'm going to want to have? Remember, what's for the Zaitsev rule? There's two parts of the Zaitsev rule. The more substituted part, which that's not an issue here because we only have one type. What's the other type? What's the other thing we worry about with the Zaitsev rule? E and Z, right? The E and Z part, the stereochemistry part. So we want to make the alkene such that the big groups, the higher priority groups, are farther apart. So this alkene, if we did it, the higher priority groups are on the opposite sides. So this is a E alkene. That's also what happens in E alkene. So we want to form more substituted double bond, and we want to make the E alkenes as well. And that's what we did here. There's your E1 reaction. Balance my charge. What else did I make? I made right. Don't forget to also balance your charge and show right the oxygen lone pair took the hydrogen that made the pi bond. So you have plus charged methanol with that extra hydrogen on it. Renumber my carbons. 1, 2, 4, 3, 5, 6. There's your E1 product. And so one common error people try to make is they'll get to this and they'll see, oh my God, there's a benzoic position. I gotta get there. You can't shift. You can only do the rearrangements when they're 1, 2 bonds away. 1, 2 bonds away. So you have to do both steps. You can't all of a sudden have the hydrogen here just jump. You can only do rearrangements 1, 2 bonds away. Look for the hyperconjugation buddies. They can do the rearrangements. If it's 3 bonds away, it won't work. Right? It has to be 1, 2 bonds away. Right? I can't move. The hydrogen on 6 is 1, 2, 3 bonds away. It's too far away. I can't do the rearrangement there. You can get there, but it's going to take a couple steps.